Welcome. I'm Dr. Dave Turner. I'm the application scientist for the BeoCat cluster computer at Kansas State University. We also help manage the BeoShock cluster computer at Wichita State University. I've already posted some introductory videos on BeoCat and BeoShock, as well as an introduction to Linux and Bash programming, and covered some advanced uh, usage of those systems. I want this presentation to be more on performance. What is a high performance computer? How you get performance by using multiple cores and multiple compute nodes, and other aspects that affect performance. So this is a diagram of the BeoCat cluster computer where we have two head nodes, Clymene and Helios, and about, I guess, 310 compute nodes. Now we colorize them at the bottom as different families, with the Warlocks being AMD and the others being Intel processors. So I'm not going to go into much detail about this other than to refer back to some of the types of uh, uh, nodes that are in there. These are each high-end server nodes, so they are uh, multiple. So we have multiple compute nodes, we have multiple cores on each node, uh, and we have 170 GPUs in BeoCat as well that can be used, in our case, not to do graphics, but to accelerate scientific codes. This is BeoShock. It's a smaller system, 768 Intel cores on 21 compute nodes, but likewise has uh, multiple nodes for parallelism, multiple cores per node, typically 36 cores in most of these nodes, and has 8 GPUs in there for accelerating scientific apps, and is connected by 10 gigabits per second Ethernet network. Okay, I'm going to cover this mostly uh, from a historical perspective, because if we do that, we see the uh, slow addition of uh, complexity and capability in doing things with greater or applying greater processing power to a given job. So one way to use these large cluster computers is to simply run more jobs, but at times we want to run one job on the entire machine, or usually more often a big chunk of the machine. And again, that can be done by using multiple nodes, multiple cores on a given node, by applying GPUs, things like that. So if we go back to the beginning, things were fairly simple. A scalar computer. Scalar just means doing one thing at a time. So if we take a real simple algorithm, and that being a vector addition here, at the bottom, you can see that all we're doing is taking a vector x of elements x0 through x whatever, n minus 1 to be abstract, and adding that to the vector y to get the vector z. That means that you do one thing at a time. In this case, we're pulling x0 up into the processor and putting it in a register from main memory. Then we pull y0 up. Then when both of them are in the processor in separate registers, we do an addition on them to get z0, and then that gets pushed down back into the programming data. So very straightforward. You do one element at a time, and then in your next iteration through the loop, you do the next element. X1 gets pulled up, Y1 gets pulled up into another register. You do the addition to get Z1, and that gets pushed down. So simple and easy conceptually, uh, but uh, we can do things a lot faster using of uh, a lot more complexity in the processor itself. So uh, here's an example of this algorithm, and on the left is the code in the language C. If you don't understand C, that's fine. Uh, for the most part, uh, a lot of this is setup. The first part, the main is the function up there, and we define a few variables, n being looks like about 1,000,000. So we're going to take vectors of size 1,000,000 in order to do this. The next section down there, we're actually allocating space for the X, Y, and Z arrays or vectors. And so we're specifying the size as n times the size of a double precision number. So a double precision number is 64 bits long. Then we're initializing things. X sub I is just going to be the double precision of the index I. So it'll be numbers from 0 to 1,000,000 minus 1. And then we're doing the same for Y, but we're setting it as I squared. Okay, the next section is where we actually do the work. And that's all that you really need to concentrate on. We have a loop for I equals 0 to uh, uh, up to 1,000,000, and then we're incrementing it by 1. So this is where we step through and do our vector addition. Z sub I equals X sub I plus Y sub I. And again, in the scalar computer here, we're just doing that one element at a time. And so it's fairly straightforward. So this was originally, this set of slides was originally made for a workshop. I do not have this sample code in there now. If you do want to try compiling these and running them, just send me an email and I can send you the actual code or put it somewhere where you can grab it. Since this is C code, again, I think I'll skip the directions on how to compile and run the C code there. The directions here are compiling it with the Intel compiler that's in IOMKL module. You use ICC. And then on the bottom there is doing the same with the GNU or the module load FOSS and then the GNU compiler GCC. Okay, so what came next is called vector computers. The idea is rather than doing one thing at a time, we want to do a lot more things at a time. And Cray came along and invented these vector supercomputers. You can see them in the pictures down at the bottom. These were typically about $10 million computers, and Cray kind of had the market monopolized at the time. They created these things and were the only ones selling them. Later on, other companies came and did variations on this. I worked on one called an SCS-40 when I was a graduate student, and that was an air-cooled version of these. These are liquid-cooled, and they were just kind of knockoffs. They used the same kind of compilers and everything else. But the SCS-40 was much less expensive. We had one that was like $250,000. The idea behind these is that you do things 64 things at a time. So it's all done by vectorizing the big loops in your program. So uh, to do our vector add, if you look in the upper right corner, uh, it would pull 64 elements of X from main memory into your vector processor. And you can see that I've drawn the line going between the processor and memory is much fatter in this case because you're loading 64 things at a time rather than one at a time. So the bandwidth between the vector processor and main memory was necessarily much greater. So you pull in 64 elements of X, 64 elements of Y, and then you do those vector additions at the same time. And that's conceptually uh, in order to get Z0 through Z63, and then that gets pushed down back into your main memory. Now, I say conceptually because they aren't done exactly the same time. It's actually done in a pipeline manner, which is very efficient. So they might be done in the same clock cycle, but doing an addition or another operation is a multi-step process that's handled, again, within one clock cycle, but it's handled internally within the processor. And to the user, it just seems like it happens all in one step because it's in the same process, the same clock cycle. But since it's done in multiple steps, you can be doing the first part on X0, and then when it's done, you can be doing the second mini step on X0 and Y0 while you're doing the first step on X1 and Y1, and then go on like that. And so you're overlapping the mini steps that are done within a given clock cycle to make it look to the user like you're doing 64 things at the same time. In order to do 64 things at the same time, they have to be independent. So your loop has to be doing the same thing, meaning not doing real jumping around with go-tos and stuff like that. So you're doing processing on data at the same time, but one pass through the loop can't depend on the previous pass through the loop. So if you're doing one pass through the loop and updating a matrix that's used to start the next pass, that is not something that's parallelizable or vectors or can't be vectorized at all, and you have to do that in scalar. But a lot of things in science you can do independently in this manner and vectorize it. So the goal of this is then to do things 64 times as fast. And the Cray vector system was good at doing that. The processors themselves were also very fast. They were made of gallium arsenide, which is faster than silicon. It was also much more expensive to do things with gallium arsenide as well. But this was kind of came around in the 1980s time frame, maybe a little bit before that. And so this was the big thing for really being able to apply a lot more power to a given problem. So one thing about doing vector computing, this really applies to any parallel computing. Some of the types that I'll get to in a moment are that, let's say you have an application that has 3 loops, and the loops take 30 seconds for the first one, 20 seconds, and then 50 seconds for the last one. If vector loop 1 and 2 are, if the loops 1 and 2 are vectorized, but loop 3 can't be because it has a dependency in it, then your ultimate speed for that job is going to be 30 seconds divided by 64 for the first loop, because we're speeding it up by 64 times, ideally. And then 20 divided by 64 for the second loop, but that third loop is going to kill us because it's not vectorizable. So it's going to take the full 50 seconds. So your overall time is going to be 50.78 seconds. So you're basically going to double the speed when your goal is to get it somewhere around 64 times the speed. So if all three loops are vectorizable, then you can see you can get it down to 1.56 seconds, which is again your 64x speed up. Now, there are going to be scalar sections in between the loops, but usually those are not that significant. So, if you get a 60 times speed up by using a vector computer that can potentially get 64 times speed up, then that's very good. You're still getting the majority of the potential that's there to speed up your algorithm. So this is true for vectors. This is also true later on when we get to speeding up codes by other methods, like using multiple compute cores and multiple nodes in a larger system. So ultimately, your speed up is going to be only as good as your worst loop. Okay, so in the 1990s, people were looking and saying these Cray computers are great. And again, there were starting to be some knockoffs that were less expensive, but still, there were so many powerful workstations coming of age that people wanted to use those to try to compete. And so people started using, again, PCs, but more powerful workstations to work on the same program. So this is where cluster computing came about. Cluster computing is the coupling of multiple computers with a common network interface, hopefully a very fast one. So there's a large bandwidth, meaning you can put a lot of information across, and with a low latency. Latency is the minimum amount of time to pass a small packet. So this is a diagram of just a simple two computer or two compute node cluster. So we refer to them as nodes or compute nodes, but they are simply computers of whatever type. I've done a short workshop where we actually made a cluster out of the PCs that people had there, or we gave them desktop machines so that we could use the Unix operating system, which is a little easier to deal with for some of this clustering than if you had a Windows system, for example. So nowadays we have network switches that might be 40 ports, and you can go beyond that with different topologies as well for the network switch. The communication rates are 40 to 100 gigabits per second. And again, the latencies have gotten down to where about 1 microsecond is all it takes to communicate a small message like 64 bytes or so. Now, these are tricky to program, though. So the programmer has to be the one to distribute data between the nodes and decide how to communicate data across the nodes. Because to do any calculation, you have to have the data in the same place. So this is no longer a shared memory system like the vector stuff is. You're actually running the same program, but copies of the same program on the different compute nodes. And so this is a difficult kind of programming to do to parallelize something across compute nodes, but that's what we had to work with back in the 1990s. So if we just take the simple example again of the vector addition, then you as the compute programmer would have to decide how to divide the vectors up. And what I've done in this case is I've chosen to take all the even numbered elements and put them on computer 0, and all the odd number elements and put them on computer number 1. I could just as easily have decided to put the first half of each vector on computer 0 and the second half on computer 1. It wouldn't have mattered in this case. To do the actual addition is trivial in this case because all the elements that you need are on the same node. So there doesn't need to be any communication between the two computers. That's almost never the real world case. There's almost always the necessity to communicate between the two compute nodes during the algorithm. I'll show that a little bit later. So in this case, we would just be doing all the, well, it would take a little effort to start the jobs up on the different nodes. You have to have a script that sends the information and data out to the various nodes. Once it's there, the computations can be done independent of each other. And then at the end, you might want to communicate the result back to one of the nodes to print it out or save it. But otherwise, this would be a very simple program. So I want to give you just a little idea of what a more complicated program would be without going into too much detail. This is a matrix multiplication. This is conceptually very easy to do. If you wrote this out, it would be a 4-line program, basically, the core of it would be. And it's doing the summation that's in the upper right corner there. So to do a matrix multiply, you have 3 nested loops. So you'd have your 4i loop, your 4j loop, and your 4k loop. So the 4i and j would loop through your elements of z, and your k loop would be doing the actual work of the multiplication, and that would just have your x element times your y element. So this is where you multiply one column by one vector. So in a scalar computer, this is real easy to write up and run. To do this on a multi-node cluster computer is very difficult. Is at least more complex, we'll say. The best way to do this is by decomposing things by subblocks. And so the diagram below is showing that the subblocks of X, Y, and Z that are in red are assigned to compute node 0 to start out with, and the ones in green are assigned to compute 1 and so forth. You could, at the beginning of your program, broadcast all of X and all of Y to every node, and then start with a 0 matrix Z on every node, but then you would have replicated data. And so you would be having the entire X, Y, and Z matrices replicated. And this might be fine if you had small matrices, but when you get to having very large matrices, you just can't replicate the data like this because it wastes your memory space. And so doing this in subblocks allows you to keep just one copy of the data at one point, but it means that in order to do the calculations for Z, you have to pass the data in the X subblocks and Y subblocks around. And someone a long time ago worked out the best way to do that. And you do that in the method that is in the list there on the upper left. And that's, you start by broadcasting the diagonal blocks of X down each row. So the diagonal blocks of X would be the X0 through X11 there, as well as the purple X2 through X33. And then you multiply those X blocks by each node's Y blocks. and then you shift the Y blocks to the node above it, and then you repeat with the X blocks to the right of the diagonal. Now, we only have 4 compute nodes, but if you had 16 compute nodes, then you'd have 16 subblocks of X and the same of Y and Z. And the number of steps here of communication and calculation would get um, more complex and so forth. But you follow the same recipe of each time broadcasting the diagonal blocks of X down each row. So there's copies of them on the entire row and multiplying them by the Y and then rotating or shifting the Y blocks up each time. Then you keep the replication down a fair amount and minimize the communication. You can also do tricks like hiding the communication behind the computations. So you can do the communications asynchronously and be communicating at the same time that you're doing the computations and try to hide that because the communications otherwise would lead to inefficiencies. So I don't want to give you the exact code here because it'd be many pages long. You can look up the algorithm if you really want, but I just want to illustrate that since I'm using the very simple vector addition as an example for a lot of this, that things do get a lot more complicated, especially when you're talking about multiple compute nodes. So I mentioned that dealing with multiple computers like this, you have to pass information around. It used to be that there were a lot of different software packages that allowed you to do this. Now there is a standard called MPI for Message Passing Interface that is used on all systems. And the example on the left is again in C, but other languages have something similar. Python, so on C, C++, and Fortran, they have very extensive MPI libraries available. On other languages like Python, there's more stripped down versions that just cover the basics, but that's the basics that most everyone needs anyway. So uh, uh, if you're doing the MPI for Pi library, again, they really only have the simple stuff, and that's really all that you'll probably need anyway. Other languages do have other functions, but they often are very similar to this. The highlighted and background yellow are the MPI functions. So I'll just go over some of this briefly to give you a taste or flavor of what is involved. When you run a code, when you compile it with a function like MPICC, and this is just a script around the Intel ICC compiler. And so it adds in the MPI stuff like the library and so forth that you need to do the message passing. To start a job, you would do it with an MPI run command and give it the number of processors or number of nodes that you want to run on, and then the application. And that's again just a script that will launch the code, but it'll launch that many number of the code on different cores or different compute nodes in this case. So that would actually S-copy the code over to the remote nodes and start it running there. So you would have 2 copies of this particular job running, one on each of the computer. Even though they're the same code, they would be operating on different data because they're on different compute nodes. So the first part of each MPI code is kind of the handshaking stuff. It's the MPI init that just allows MPI behind the scenes to communicate and do the initial contact with the other the other MPI tasks. So in this case, we're just running 2, but if you can have 1,000 nodes and run 1,000 MPI jobs, one on each node. And so it can get very complicated because you have so many different tasks. And the MPI system just keeps track of those for you. The MPI com size returns the number of processors into the variable nprocs there. And then the rank, uh, each one is going to have their own individual rank. So I call it myproc, and some people call it a rank or iRank or something like that. But that's going to be a number from 0 to nprocs minus 1. And each copy of the code is going to have that be different. And that's how your program is going to operate on a different section of the data. So you as the programmer have to decide what part of the data, how it gets divided up, and that's all done based on that element. This particular program just sends a message from one computer to the next, and then that waits for it to be received and sends it back. So the conditionals down there say if my proc is 0, I'm going to initiate this and do a blocking send to the destination. And then I'm going to do a blocking receive and sit there and wait for a message to come back. So the else statement means that the second process on the second compute node is going to do the receive first. It's going to sit there and wait until it gets a message from computer 0. It's going to increment the token once and then send it back. So that's all we're doing is passing a variable or from computer 0 across the network to computer 1, adding 1 to it and sending it back. But this gives you a little idea of the manual nature of using MPI to send data between computers. And again, if you have to divide up the workload on each computer system and manually pass data, you can see that this can be very complicated to orchestrate all the passing of the messages. And again, there are tricks to make these algorithms efficient by doing, instead of blocking sends, do asynchronous sends that can be done while you're doing computations as well. So parallel computing with cluster computers, what I showed you is fairly simple. They commonly have about 40 ports, so you can plug in 40 computers to them. And that's a flat network because every computer can talk to every other one without being blocked. That's not always the case when you get to larger systems. And systems can have tens of thousands of compute nodes or even hundreds of thousands and fill up a warehouse. So we're talking about, 50 to $100 million computers in these cases. The lower part here is describing Blue Waters, an IBM system that used a network that has a topology. So it's not a flat network where you are guaranteed that all nodes can be talking to all others without any limitations. In this case, it's a 3D network where every node can talk directly to the ones to the left and right, in front of and behind and up and down. But it's a torus in that it's wrapped around on the edges. So the nodes at the edges can talk to the ones on the other edges. In other words, it has periodic boundary conditions in that they wrap around. The network wraps around. So this is an expensive system, but it's very scalable in this way, in that if you have a given system size and need more power, you can double the size of the computer by adding more racks onto one end. And that would essentially just add more to one side of the diagram down below. And then if you're running a bigger system on it, you can do that efficiently if your code is communicating with just the neighboring nodes. And this is called a distributed memory computer. So that's one of the keys for this type of a system is that you want to run an algorithm that is distributable like this and not something that has to communicate in a more tightly coupled manner where every node needs to communicate at some point with every other node. So you want to communicate more by shifting data in a direction or localized communications rather than doing all to all, where a given node needs to broadcast to all the others. The upper diagram there is a multiple layered switch that you could use in a cluster where you use smaller switches. In this case, I just used 4-port switches to uh, illustrate how you could get a non-blocking all-to-all by using 8-port switches to do a 16-port all-to-all cluster. So this would be useful if you did have more uh, of a tightly coupled application or sets of applications, but it gets expensive very fast to build up multi-layered switching networks like that, especially if you're talking about using 40-port switches instead of 8 ports. So on Beocat, on Beoshock, it's fairly easy because there's 21 nodes, so they can all be plugged into the same switch. On Beoshock, sorry, on Beocat, so Beoshock is easy because of the small size. Beocat has 310 compute nodes. And again, our switches are 40 to 100 gigabits per second, but 40 ports means we can only plug 40 things in at a time. So what we do is we plug 40 into one switch, and then there's a couple ports out the side that we link in kind of a circle. So we can communicate between ports with on one switch to another, but that's a real big bottleneck because if you have 100 gigabits going into the switch from each node, but only 1 or 2 links going between switches, then if you had all of your nodes on one switch trying to communicate with all on the other, well, they can go up to the main switch at 100 gigs, but then uh, there'd be a conflict for the 200 ports lines going between the switches. So you'd be losing a lot of performance if your job was multi-node and spread between switches. So on Beocat, if you are running multi-node, Slurm does try to put you on the same switch. And it does give you a bit of a warning if it can't do that. But you can get a performance hit by that. So just be aware that network topology comes into play when you're talking about especially scaling up to these large supercomputers or larger cluster computers. Okay, the next evolution came in that instead of each compute node having one processor, they started adding a second processor in, and then 4 processors and so forth. And now the Intel processors can get up to 64 cores, and the AMDs might have 128 cores. So we have some of those in Beocat, for example. Most of the nodes in Beoshock are Intel and have 36 cores. So this means you have 2 levels of parallelism that you can exploit, which is great. You can run one job within a given compute node so that you don't have to do MPI, but you still can take advantage of the multiple cores. And this is easier to do than using MPI because you have a common shared memory there. So you can run one program and have one set of data. You just have to make sure that the various cores, when they're doing their work, are not trampling on the data. So it is easier to program. You can run your MPI programs on this and have one MPI task on each core, for example. So that is commonly done. And then each MPI program would have its own memory space, and you'd be manually copying between those spaces when you do your send and receives. But OpenMP is multi-threaded package, and that's an easier way to program for shared memory and more efficient since you're not passing the memory around. You're not doing the memory to memory copies. You just have to share that. And again, the OpenMP package makes sure that you don't trample on data so that if one area of data or one variable is getting updated, you have to do an atomic lock when you access it so that only your process can update that and it doesn't get trampled on by other processes. So the diagram at the bottom is a diagram of what a program might look like over time as you go from the left to the right. The scalar parts are all done by the master thread. And then when you hit a parallel region, like your loop, that's where you would get it divided amongst the cores that you have. So this diagram shows it dividing amongst different numbers of threads, each thread going on to a core, typically. But more likely, if you have a given number of cores, like if you had all 16 cores available in the diagram to the right, you would want to make use of those. And so you'd have one thread running on each of 16 cores, and each of those threads would be doing 1/16 of the passes through that loop. So it'd operate on 1/16 of the data. And then when you're through with that loop, you collapse down and the master thread does the scalar part. And the next time you hit a loop, again, your various threads will do the work separately. So less communicating between the stuff here. So this again is the very simple example of the vector addition. The only point to look at is down where you see the yellow towards the bottom, and it has a pound sign and then pragma OMP parallel 4. So in this case, it's fairly straightforward to convert our scalar code to a parallel code. That's the core of the work down there, is we simply put a pound sign, which will be taken as a comment to the compiler, and the pragma says OMP for OpenMP parallel 4. So I'm going to parallelize the for statement that follows. So we're going to parallelize the vector addition there. Now, the first thing I do there is I put if I equals 0, I'm going to print out n threads for this loop is % of %. So I'm going to print out the number of threads and the maximum number of threads. They're both going to be the same. And if you look up above, I do set the number of threads manually in this case to 4. And then, but you can let it, if you don't put those in there, then it'll just take all the cores that you have and put one thread per core. You can also set this stuff with environmental variables outside of your program. And that's shown on the bottom right where it says export OMP num threads equals 2, for example. But this shows you that OpenMP programming and parallelizing can be much simpler. Now, this is a very simple example. The pragma can have arguments there, and you may have to put more information in there to get the loop to parallelize well. But if it is independent things being done, it can be this simple to put in multi-core programming. And again, OpenMP is the most common package for C, C++, and Fortran. For Python, there is an equivalent uh, uh, MP for PyMP is what it's called. So you can pip install PyMP and get, again, kind of a stripped down version of the OpenMP library, but it's actively developed and maintained, and the stripped down version is all you really need. Other languages do have variations of this, and you'd have to look those up, but I'm trying to concentrate more on some of the uh, concepts here of what computers do and how you can apply more power each time. So in this case, again, we can now apply the multi-core capabilities of each compute node, as well as if you wanted to, you can apply the multi-node still. So multi-core clusters, again, we're building up the complexity and the capability as we go. So again, multi-core clusters now are just made of multi-core nodes. So these are shared memory within each node, but then distributed memory between the nodes. And again, if you wanted to program one code to take advantage of both multiple nodes and multiple cores within a node, you can use MPI between the nodes and MPI between the cores. This is easier because you're only doing one level of parallelism. It can be less efficient because you have to then pass data manually between the memory spaces within a node. That's pictured on the lower left there, where each thread or each task of MPI has its own memory space. A lot of codes that have been around a long time still do this because it doesn't really hurt efficiency all that much in some codes, and it's easier to maintain with only one level of parallelism. The second method is where you would have both nodes as if they were on the right, where you'd have shared memory on each node then. And again, that would be more efficient for some applications because you're doing very efficient shared memory on each one, but you'd have to do two levels of parallelism, MPI to pass between the nodes and OpenMP to do things within the node. Okay, we're getting even more complicated here because uh, each of the cores can also do vector stuff now. It's not as good as the Cray vector stuff. The Cray vector stuff, uh, the compilers were very good. The hardware was geared very specifically to do vector stuff. And today's more modern vector units can do, I would say, simple stuff in vector. But as you see, the vector speedups are much smaller. They can do 4x, 8x, or maybe 16x speedups, but it takes a lot more work. And uh, just because the hardware itself doesn't do the pipelining as well, uh, it you have to make sure that the elements are aligned and other things like that. So the bottom left kind of shows some of what I had to do to go through and get some simple things to compile and run in vector. Even though the vector units are on most modern processors, I don't see a whole lot of speed up coming from them unless you're using some of the built-in optimized libraries. And it is very common from the software side to use like the BLOS libraries, for example, that are basic linear algebra subroutines to do simple tasks like matrix multiplies. And those are at times hand-tuned and do use the vector units very well. But just taking raw code and trying to put in the vectorization yourself, if it's a code that you wrote up, and can't use those built up libraries, I have not been able to get a lot of uh, good results out of that. And it does take a lot more effort than certainly it did with Cray computers. Okay, so I didn't really touch on the GPUs, so I'll just mention those briefly. GPUs were designed to do graphics processing, uh, but we use them to do, they are streaming processors. They're good at doing lots of things at the same time. And so that works for some applications. We use them a lot on Beocat and Bioshock for doing classical molecular dynamics, where you have millions of atoms that are just jostling back and forth. And so they work very well on GPUs. Also, a lot of they have tensor cores on them, so a lot of training of AI models and stuff like that work well on them. So that's a level of complexity that we have on both Bioshock and Beocat as well. It's a different type of uh, parallelism. I want to talk some more about uh, performance in computers. Now, even when I started back with the simple scalar computer, uh, things of things that are going on behind the scenes are a lot more uh, complex. Um, I drew as a single line the pathway between memory and the processor. But actually, there's multiple levels of memory cache, each that's faster than the previous one, that it's good to be aware of if you're having to look into performance issues. And most of these are managed by the system itself, so you can't manually manage them, but there are often some pitfalls that you can avoid uh, or doing things that can help performance. Uh, it's helping the system to get good performance rather than manually telling the system what to do. So when in our demonstration of the scalar uh, system and doing something as simple as a vector addition, what I said is you start by pulling X0 up into the processor and putting it in a register, and then you pull Y0 up. In modern systems, that's not what's done. If you access X0, you access a whole line, a cache line. So it's a whole set of elements that get pulled up. So you might pull 8 doubles up, for example. And as you pull it into the vector or into the register in the processor, copies are made at the different levels of cache. So it would leave a copy in the L4 cache, the L3 cache, L2 cache, L1 cache. L1 cache might be or is typically very small but very fast. So again, I have the numbers, some typical numbers on the left there. You might have 168 registers for each compute core. There might be 128 kilobytes in L1 cache, and it's very fast. So if you're reusing data, if you have a program that can reuse data, so a matrix multiply, for example, when we did the subblock decomposition, is using each subblock of the X matrix multiple times, and the same for Y. So you want to have your algorithm pull those subblocks up and reuse them as much as possible before they need to uh, get different subblocks. Now, you may not have room in the 128K that's in your L1 cache to fit the whole matrix, but by pulling some of the subblocks in and reusing them, you don't have to load them each time from main memory, which again in yellow here is about 17 gigabytes per second. You get 700 gigabytes per second if you're going from the L1 cache to the processor. So what I want to illustrate here is that with these different caches, even though they're managed by the processor itself, you can write your algorithm in a way that reuses the L1 caches or the low-level caches that are much faster to speed up your code. Uh, this is more the type of thing that I would do if I looked at a code and saw I might see some things that would tell me that it's uh, very much not optimal in that it's not uh, making use of reusing the data when it gets to the lower level caches. So it's just something to be aware of when you're talking performance, that there are these layers in there, even though, the system does a real good job of managing those for us. So I kind of went over this that in all the parallel computing, not just vector computing, your goal is to get an n time speed up on n processes, whether that's vector or whether that's multi-node using MPI or uh, multi-core using OpenMP. And I've put some links to some good tutorials there that give more broad descriptions of them if you're interested in looking at them. Um, when you talk about communication, especially between compute nodes, uh, the communication rate and the latency really do affect how much you can do. Because if your communication was infinitely fast, then you could spread any job over any compute nodes and get 100% efficiency. So the communication is what's going to hurt your efficiency. Uh, Communication between two nodes and also any conflicts if you're trying to communicate too much across too many nodes, for example. The diagrams on the right are just some communication benchmarks from the NetPipe benchmark that I've developed over the years. And this kind of shows that the communication for small messages, the bandwidth is very small because it's dominated by the fact that there's about a 1 microsecond latency between compute nodes. So if you're passing a small message, then you're not going to get a very good rate because that latency is going to dominate. But if you're passing a large message, then you'll get, in general, a good bandwidth or good communication rate because that latency isn't so much dominant of the overall time. Mainly what I want to illustrate here is, yes, faster networking, like doing 100 gigabit per second rather than 10 gigabit, is always going to be better. But just be aware that when you go multi-node, your communications are going to take longer because the latency is going to be longer and the bandwidth is going to be less than if you're doing things within a compute node where you're doing either sharing the memory and not copying it, or even if you're doing MPI and just doing memory to memory copies. So if you are going to run on multiple compute nodes or multiple cores on a node, the first thing you want to do is do a scaling study. And this is showing a scaling study of running the same test job on 1 core, 2 cores, 4 cores, 8 cores, and 16 cores. I tabulated the run times there, and then I calculate by hand the speedups. So on 2 cores on this particular application, we get a 2x speedup, which is ideal. But when I go to 4 cores, I get 3.6 where we'd like 4, and so forth. On 16 cores, you can see that I'm getting 9.1 times speed up, where we would again like 16 times speed up, which would be ideal. So when you run on multiple cores, question is how many processes should I run on? Or how many threads, how many cores? And the answer here is, well, your efficiency is dropping quite a bit on 16 cores. It's not so bad on 8 cores there. You're almost 7 times speed up on 8 cores. That's reasonable. I would stop here and run on 8 cores because on 16 cores, you're only getting a little above half for your utilization there. You can do the same thing or should do the same thing if you do multi-node before you do a whole bunch of runs. Run on one node, two nodes, four nodes, and do the same kind of uh, a study of the scaling. So do keep in mind that multi-node jobs can take longer to get through the queue. Also know that on Beocat, if you're not running on nodes owned by your group, then be aware that your jobs can be preempted by someone who does have priority on those nodes. So if you try to run on multiple compute nodes, uh, it just increases the likelihood that one of those nodes will get preempted and then your whole job will fail and get re-queued and run from the beginning. So I've seen people try to run on dozens of compute nodes that they don't own. And in that case, I almost tell them, just give up, because if you're going to run for any time, it will get preempted and fail to run. Sometimes running across multiple nodes is necessary just to distribute the memory if you can't fit the entire job on one node. So there are good reasons to run on multiple nodes as well. Okay, people do ask, if you're running an environment where you're running, where you're sharing your node with other jobs, do they affect each other? And the answer is really not much, if anything, that I've ever observed. When Slurm allocates your resources, you get those allocations. So if you ask for 16 cores on one node, nobody else, no other user is going to be using those 16 cores. If you ask for one GPU, that GPU is yours. There are shared resources in that if you ask for a certain amount of memory, you have that memory allocated to you, but there is only a certain amount of memory bandwidth between main memory and the processors. So you are sharing memory bandwidth to the processors, but that's usually not a bottleneck. And so that's not something you need to worry too much about. It could be that the network connection, if you're doing a multi-node job and someone else on the job is using multiple nodes, and then you'd be sharing the communication channels, that could slow things down. But we really don't observe that on Beocat or Beoshock because not many people are using multiple nodes. The one interaction that we do see is that if people are using the file server, and the file server itself can slow down. We don't see that so much. There is limited bandwidth going from a given node to the file server, but that's enough that that's usually not the bottleneck. But again, someone can hit the entire file server hard enough that can slow things down. But then Nathan, as our HPC system administrator, monitors that, and he would typically limit the number of jobs that another user could run at the same time, just to make sure that this doesn't happen. Okay, I think I'm going to skip some of this stuff. It's always good to put application or programming in your application. I've done that manually in some of the applications I've written up. There are also tools, like Python has some good tools in it to automatically do this kind of application programming or profiling, and also one for memory profiling that can be very useful if you're trying to optimize the performance of a given application, because it tells you which loops or functions the code is spending its most time in. And then you can look at those and concentrate your efforts onto understanding what might speed those things up. If you do need to optimize programs, get in touch with me in particular. That is what I do as an application scientist, and I've got over 3 decades of experience in doing just that. Okay, additional information. Uh, I've posted, as I said, introductory material and videos on both the BayoShock and BayoCat websites. These are some other sources that are very good for covering MPI and OpenMP, as well as one for covering parallel computing. I'll also probably make a more in-depth, like I'm developing half day workshop for software carpentry that goes more into uh, performance in not just C, but in other languages as well. And so I'll eventually probably record that, but that'll be a full day tutorial uh, that I'll post, and that may not be very quickly. So these are some other sources that you can look at with information. And of course, always feel free to contact me if you have questions over this. Otherwise, thank you, and I hope you found this useful.